Just want to make sure I got something. Well, we're not really what I'd call a full group. We got like four of my students. So either way, I got to go ahead and get started, guys. I wish more people would turn up. I hope that's not a indicator of what's happening. Please go ahead and chat me your first and last name so I have you on roll, and we're going to go ahead and get started. I wanted to make sure you guys noticed that I did make the second online test and that I made the date quite a bit different than what you might have expected. In other words, I gave you a little bit more time. So currently the situation is you have a practice test called PT. It's currently called PTO3, but I'm getting ready to change it right now as we speak. I'm changing it to PTO2 because it's really the second test. And that is the practice test for the second test, which is an online test, and that covers chapters 19 and 20. That practice test will disappear on October 7th, and the actual online test is in the online test module, and that one is also currently called online tests or OT 03. I just changed it again to O3, OT 02, but that's due at 11:59 p.m. on October 7th. So make sure you get that knocked out on time. Uh, what I'm currently leaning towards is we will have a face-to-face test on Thursday of, well, I say it's tentatively Thursday of next week, but what's going to happen is next week we meet on the 8th and the 10th. And I'm going to probably open the test either on the weekend or Monday, maybe Tuesday at the latest, but I'll open up the test and it'll probably give you Monday up until the following Monday. That's going to be a face-to-face test that you have to get proctored. There are ways you could get me to proctor it by coming on campus, but you can also go to any one of your campuses testing centers, but you'll have to make an appointment and see their rules and see their times. Every campus has at least one night a week that their testing center is open rather late. So hopefully that'll work in your favor. If you can't find a time to take that test during that roughly 6 or 7 day interval, make sure you let me know and I'll try to work out something. It might be something where you can just, come on to campus, or we might have to start looking for services in your area. I don't know. I don't think any of you are really a very far distance away, but I might be wrong. Some of you might be a really far distance away. And if that's the case, then you might have to look into getting a local service, a local school or something to proctor you. So I just want to make sure that was known. I did push the due dates back on the homework as well. I think everybody had gotten chapter 19 done. If you didn't let me know, I'm willing to give you another night on chapter 19 because it was due last night at 11:59, but I can make it due tonight, or I'd probably be okay with even tomorrow at 11:59. So if anybody needs that extra time on 19, no one's asked me for it. I'm just doing it out of the goodness of my heart. And then chapter 20, which we should be done with, I think I've moved that to be due either Sunday night or Monday night. It's supposed to be Monday night, but as that's the normal frame for you guys. But not sure if I'd set it to Monday night or Tuesday or Sunday night. So check that out to find out yourself. Remember, you're wanting to test the actual due dates. You expect them to be correct on Pearson, not on Canvas. Does anybody have any questions about any problems we've had so far, or any kind of practice test questions or something like that? I will let you know I did do an office hour with with a couple of my 202 classes. Now they're the algebra-based class that's the same as this one, but it's algebra-based. That being said, the problems they asked are very consistent with the problems that you have to do in this class as well. So if you look on my YouTube channel, there's one called Solving to Coulomb's Law, parenthesis, electric field, close parenthesis, problems. I think I meant to put the electric field after the word problem. But anyways, that's actually an off-scheduled office hour that I did with two of my 202 students, where I work some pretty good, helpful Coulomb's law related problems that are related to the stuff we're doing now. So you can definitely, or that we're going to start doing now. So you can definitely check that out. Of course, I'm hoping you all subscribe to my YouTube channel. That way you'll get an email assuming you have it set that way, you'll get an email every time I post a new video. I posted 2 new videos today, so I might even post more tonight, but I'll definitely be posting some more later this week. We are starting into chapter 21, which is on charge and Coulomb's law and the electric field and a bunch of stuff like that. Well, I want to let you know that I really would like to spend a lot of time to explain the concepts as much as possible, because the concepts are really interesting and it's helpful to know. Your book does a good job explaining it, but I want you to look in our uh, Canvas course. And in Canvas, you'll see that I have in week, I believe it's week 4. Yes, it says week 4. You'll see there is uh, a URL. That's a link, an internet link to Veritasium Electricity Explained. That's a really good explanation of what actually happens when you connect some kind of battery, the positive terminal to one end of a wire, and the negative end, excuse me, and the other end of the wire to the negative end of the battery. Uh, that's a worthwhile thing to know. That has some really good concepts in it. But the most important thing regarding the concepts in this class is a video that's called MIT Charge Demonstration and that kind of stuff. So if you look in there, he does several demonstrations with a Van de Graaff accelerator. There are some videos of me actually explaining that video on YouTube, but I'm not sure if they took it down because I actually was using part of the MIT video, and normally they, get you from borrowing someone else's stuff. So I might have to make my own and do that. But the main thing is I want you to watch that and try to predict what's going to happen, when he sets up a problem. Try to predict, hey, is that ball going to move to the right or is that going to move to the left? What is it? That sort of thing. So really do that to get some understanding of it. And also just feel free to ask me questions. I don't mind helping you like during office hours or at the end of class. And I'll spend as much time as I can to help you understand the concepts. I just don't want to use too much of class for them, because I think you can get them from reading and just your history of science in general. The main thing to keep in mind, though, is when we start to do this stuff, there's going to be conductors and there's going to be insulators, and that's actually a spectrum. So we're going to learn some things about that kind of stuff. Specifically, the things that act more like conductors are elements or compounds that tend to not have a very, very, very strong hold on at least their outermost electron. And the more of those electrons that can get loose, the more conductive the material is. If it's, one per atom, then that's a pretty good conductor. If it's more than one per atom, it's a really good conductor. And sometimes it's not even one per atom. But that being said, you can actually use that and realize that, okay, well, the conductance is a result of these electrons moving around. We'll later discover that that is the case. And in fact, the same thing that makes it a good conductor of electricity is the thing that makes it a good conductor of heat. And it's those moving electrons. Those moving electrons and their ability to run into the other atoms and stuff of that sort. So, uh, what you want to be thinking about in terms of the demonstrations and the concepts is at the heart of that Van de Graaff accelerator. That's the big, silver ball that people grab and their hair stands up and stuff like that. Basically, you can look at it like it's got a belt that's really just a big wide rubber band, and down at the bottom there's a little, plastic or Teflon type axle that it spins on. It's more like a hub. The Teflon stuff has some kind of axle and bearings through the center of it, and then the Teflon rolls around with the rubber band, and then the rubber band carries up and goes around another little like Teflon spool up at the top, and then comes back down. What's going on there is you can sort of imagine that maybe someone took a tennis shoe sole and stuck it in that bottom of that Van de Graaff, so that when the rubber band comes by, it rubs like carpet or it rubs like the rubber sole of a shoe or something like that. When you do that, then what you're thinking of is that process with a rubber band rubbing up against a different material. That other material could be carpet, or you could put carpet in there and then it'd be carpet against the rubber band, or you could put the rubber band against a different type of rubber shoe sole, that would do it. But mainly two different types of materials. And generally speaking, one material have a stronger affinity for the electrons than the other. And when that thing comes by and brushes by, one of those, either the belt or the thing at the bottom, is going to steal electrons. There's not really anything at the bottom, but what's going on is when the actual rubber band slides around the edge with the actual spool and then cuts loose, that's just as good as rubbing against a different material. So I like to think of it as if the rubber band is stealing electrons from this Teflon spool, and then you'd conclude that the overall Van de Graaff becomes a net negative charge, because what it's going to do is that rubber, once it leaves the Teflon, let's pretend it has a bunch of negative charges on it. It's either that or it has a bunch of positives. And it doesn't matter, because you're going to sort of get the same result, whether you assume it's positive or negative. It's just opposite signs of what's going on. So let's imagine the belt, after it leaves that bottom spool, is laden with a bunch of negative charges, and it rides up, rides up, rides up. It gets to the top spool and it rolls over. If you were to open up that sphere on top, what you'd see is something that looks like the really nicest, most expensive screen you've ever seen. So if you know how screen looks, it's like a wire with a wire that goes in front of it like this, but then the next wire will be on this side of it instead of this side of it. And it basically makes like waffle fries or something like that. However, instead of it being a nice screen with an edge, it actually has the ends of the stainless steel wires poking straight out, so they act like little lightning rods, and they just sort of sit there over the spool. So when that negative charge laden rubber band gets to the top, the lightning rods on the end of the little spring, on the end of the little screen material, act as lightning rods and suck. You can imagine it actually sucking off the negative charges from the band. I could have chosen some better words for that, but either way. Uh, so you now have this negative charge that's going to run down that screen, that's attached to a little copper wire, and that little copper wire is attached to the inside of that aluminum sphere. And since all the charges are the same, they're going to repel one another and try to get as far away as possible. That means they're going to all orient themselves as uniformly as they can over the top outside surface of the sphere. So that's what you picture the Van de Graaff as. And then you say, okay, well, in this scene, the guy's putting a mylar balloon, which is like a metallic but plastic balloon cover. So it's like a conductor. So if you assume the Van de Graaff is negatively charged and you got this mylar balloon, which is basically a conductive balloon, what you're going to imagine is the negative charges on the Van de Graaff are going to compel the negative charges on the balloon to run to the other side. And this side will then become a net positive, even though the whole charge hasn't changed. The total charge is still zero. It's just it's been polarized. You've induced a polarization. That's the wording. So that's the kind of stuff I'm wanting you to think about, because you're going to see him do that. And I want you to think, well, what's going to happen after he turns that Van de Graaff on? Is that going to make the balloon run away from the Van de Graaff, or is that going to make the balloon run towards the Van de Graaff? And then he's going to do it with more complex ones. So that's the kind of stuff I want you to try to be thinking about. I'll see if I can make up a video of my own without using the MIT clips. We have most of the equipment that we need anyways. We don't have like little bells and stuff like that, but I can make up stuff like it. So hopefully I can do something like that. Or like I said, you're welcome to ask me anytime. I want to be the guy that does the demos. That was always my, lifeblood when I'm teaching. But now I don't have the time to do it, because for all the responsibility is in the teaching of the class. I have to add an extra few hours a week to solve physics problems in addition to doing concepts and cool demonstrations. So anybody have any questions before we move on? So please do look at those videos, especially the MIT one. The other one's about Tesla coils and stuff like that, and they're just interesting all by themselves. I would say if that's something you're interested in making, I've often been interested in making a Tesla coil myself. I would just tell you that it is a good chance of hurting yourself and danger and even possibly death. So if you do it, make sure you're very careful and you read a lot about it and try to learn as much as you can. I have not yet been brave enough to take it upon myself to build one, though I've built a lot of other stuff that was potentially dangerous. This one I just haven't chosen to do yet, and part of that isn't necessarily that I don't know. Part of it's that I'm often just a goober, and I will like stop paying attention for a second and rest my arm on something that's 1,000 volts or something. So it's best not to do that if you're wanting to live. So, anyways, anybody have any questions before we get on to chapter 21? Okay, I'm going to go ahead and share my screen because I'm going to do a lot of talking with equations. So let me go ahead and share my screen. This is my iPad. By the way, I did just post 2 videos today on Coulomb's law, and they're basically more or less like the second problem we're going to work today. So you can see them again on the video that I just posted on my YouTube channel. Right now, we're waiting for the iPad to show up as your screen, and I'm waiting for it as my screen. So what I want to tell you is some ground rules. So Newton actually discovered a law of gravity. You learned about that in the 241 class. And I want to reiterate that Newton's law of gravity was the force of gravity is, of course, an attractive force, and that attractive force is directly proportional to the product of the masses. So it's m1 times m2, and inversely proportional to the square of the distance between them. So that's over r squared. Remember, if you have two quantities like f and m1 on opposite sides of the equals, you can compare them. And if they happen to be on the same side of the fraction bar, so the numerator and the numerator are the denominator and the denominator, then they're thumbs up, thumbs up. So what that means is if I double m1, then f should also go up. And since the exponent is 1, or you don't see an exponent, that means that if I double m1, I double the force. If I double m1 and I double m2, then I quadruple the force, 1 factor of 2 for the m1 and 1 factor of 2 for the m2. If I double m1 and triple m3, then I sextuple the force, F. Similarly, thumbs up, thumbs down behavior is when the two quantities on opposite sides of the equal. So again, we're thinking of the F that's on the left-hand side of the equal, which I haven't drawn yet, and the R, which is on the other side of the equal. And then in this case, we have the F, which isn't in a fraction, so you know you can write that over 1. So the F is in the numerator, and the R is clearly in the denominator. So that is a thumbs up, thumbs down scenario. But notice the exponent of 2 on the R. So if you double the distance, that means distance is going up, so the force must go down. But the force is not going to go down by dividing by 2. It's actually going to go down by a factor of 4, which is 2 squared. So if you had a force of 100 at 1 meter apart, then if you push them apart to 2 meters apart, the force would quickly drop down to 25 newtons because you'd now have 100 divided by 4. If you were to, for instance, triple the distance, so you went from 1 meter away, which is where it was a force of 100 newtons, and you went to 3 meters away, then the force would go down not by a factor of 3, but by a factor of 9. And of course, 9 goes into 100, basically 11.11111 times. Okay, so basically our force would drop down from 100 to about 11.1 newtons. Okay, so that's sort of the conceptual background to Newton's law of gravity. And to make it an equation, we had to have an actual constant, and the constant that we turned out using was called the gravitational constant of the universe. And G turns out to be 6.67 times 10 to the negative 11th, and that is newtons times meter squared per kilogram squared. And that's Newton's universal law of gravitation. And it's said to be universal because it turns out any two objects that have mass, m1 or m2, will automatically have an attractive force. It's only attractive. You're never going to get repulsive forces. It's going to have an attractive force, and that force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So in that sense, it's universal, but also in another sense, it's universal in that specifically there is no value of R that you can put in there to make the force 0. That means the force of gravity reaches across the entire universe. Okay. Yes, it's going to be very, very small, very, very quick, but it's going to still not be zero. Okay. So that's Newton's law of gravity, but it did come with some accompanying words. And of course, some experimental work needed to be done to determine exactly what that G was that we now know as 667 times 10 to the negative 11th. I will tell you that that means 0 point and then 10 zeros and then followed by 667. So that's a really, really small number. And the whole reason I'm bringing it up is because the law of electric force, which we call Coulomb's law, is very, very much the same thing. So let me write this. So here's Coulomb's law. And this is Coulomb's law, specifically Coulomb's law for force. So I'll write this. The reason being is you're going to see that we'll have another equation for the electric field, and then we're going to have another equation that's called Coulomb's law too, for the voltage. Okay, so right now I'm just putting force around it so you'd understand that, hey, this is the one for force. But the equation is F. Again, we would normally write like proportional to or something like that. I'm just leaving a space right now. But what I want to show you is the force is directly proportional to the product of the charges Q1 and Q2 and inversely proportional to the square of the distance between them. So that's what I mean when I say Coulomb's law of force and Newton's law of gravity are identical. If I chose to double Q1, then the force would go up by a factor of 2. If I chose to double Q1 and double Q2, then the force would go up by a factor of 2 times 2 or 4. If I double Q1 and triple Q2, it would go up by a factor of 6. And if I, for instance, made the distance between the particles go up by a factor of 3, then the force would be decreased by a factor of 3 squared, which is 9. Okay. So again, to make that into an equation, we have to put a constant in there. And there's a crappy constant that we use, and I call it crappy because all the other equations need the other version, which I'm going to show you in a second. But this is really the most convenient way when you're just calculating an electric field or you're just calculating a force is by using this, what I call crappy constant. Okay. So another way of writing it is Q1, Q2 over, and now you'll see why it might be weird that Mr. Younger referred to it as crappy. See all the stuff you got to write if you don't use the crappy constant? Okay, either way, here's the crappy constant. I call it Coulomb's constant. I will tell you that there's some ambiguity as to exactly who should get full credit for discovering this. I think the three that I remembered figuring out, I know one of them was Ben Franklin, and I know one of them was Coulomb, but I think the third one was Cavendish. But either way, all three of those people have some claim to it in that they all studied it. Yes, Ben Franklin, that we know of from American history. But in this case, the constant that I'm calling Coulomb's constant is 8.998 times 10 to the ninth newtons meters squared per Coulomb squared, because what you're going to learn is the capital C is the unit for charge, and that's named after Coulomb, so it's called the Coulomb. Okay. So that's what that constant K is. And notice the G for gravitational force was 0, followed by a decimal point, followed by 10 zeros, followed by 667. This sucker's 9 billion. So K is literally very, very close to 9 billion. So it's a really huge number. And that means, as a bare minimum, you might think that the force of Coulomb is a factor of 10 to the 20th times stronger than the force of gravity. And you get that just by dividing K, the 10 to the ninth one, by G, the 10 to the negative 11th one. And that would give you actually right around 10 to the 20th. Okay. I'm going to give you a chance to do an extra credit problem where you're going to calculate the force of attraction between the proton and the electron in a hydrogen atom using the gravitational force. Then you're going to do it again with the Coulomb force, and then you're going to take the Coulomb force and divide it by the gravitational force and figure out what that ratio is. If you do that, you'll get extra credit as well. And that's a useful thing just so you can see how much massively more powerful and strong Coulomb's law is than Newton's law of gravity. Okay. In fact, I'll give you a little hint. When you do that calculation, if you don't come up with uh, basically one followed by like 40 zeros around that much, then you didn't do it right. Okay. Now, I did show another constant, and that's the epsilon zero, which is called the permittivity of free space. That number, if you choose to use the 4, the pi, and the epsilon zero, that number is 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared. We're later going to learn a way of using, instead of Newtons and meters and coulombs, we'll have ways of using volts. And when that comes into play, we can have a nicer unit for the electric field. Instead of having newtons per coulomb, which is what we'll learn, we're going to have volts per meter. So that'll be kind of nice. But either way, you can now see what these equations are. As I told you, Newton's law of gravity came with some rules, and the rules were Newton was imagining M1 and M2 as if they were point particles, and R is the distance between those two point particles. And he went on further to say the force is attractive and acts along the line. In other words, is parallel to the line connecting the center of mass of M1 to the center of mass of M2. He did go a little further and say that when we have a spherical distribution of charge, then M1 will act just like a point particle at the center of that spherical charge distribution M1. And M2, if that's a spherical distribution of charge, it will behave just like a point charge at the center of the sphere. Now, the big thing is that means you can't calculate the force or the electric field or anything at a distance away from the particle that's closer than its radius. So if you actually have to do a calculation of what's the electric field inside of M1 or Q1 in the case of electric field, or M1 in the case of the gravitational field, then you actually have to just eliminate the area between the center of M1 and M2 out to the edge of M1 or M2. Okay. So that's the way you have to do that. And we'll teach you that a little bit with the Coulomb force. So all that stuff I just told you about Newton's law of gravity acting along the line connecting the center of mass is almost identical for Coulomb's law of electric force. So the extra wordage or verbiage that comes with Coulomb's law is that you can imagine Q1 and Q2 are point charges. Then you imagine a line connecting Q1 and Q2's point charges. The length from Q1 to Q2 is R, and that's what goes in the bottom. And the force can be either attractive or repulsive. Like charges repel. So two positives or two negatives are going to repel each other. Unlike charges attract. So if you have a positive and a negative, or a negative and a positive, they're going to attract one another. And the force is going to be along that line connecting the centers, the point particles, Q1 and Q2. But again, if Q1 is a spherical distribution of charge and Q2 is a spherical distribution of charge, then Q1 behaves, at least outside of itself, behaves just like a point charge at its center, and Q2 behaves, at least outside of its body, just like a point charge at its center. Okay, so that's the key stuff you have to get. I will remind you here that extra credit is, actually, let me write that in red so it'll stand up a little, stand out a little bit better. So calculate the attractive forces I'll say force, parenthesis, forces, attractive force, uh, attracting, or let's say holding the electron and proton together within a hydrogen atom. Okay, so our picture of the hydrogen atom is a positive particle, and then we imagine the Bohr model of the atom where the electron is traveling in a circular orbit, say, and everything I drew there is the opposite of a circle, so I'm redrawing it. So let's do a circle like this. Yeah, that looks perfect. Okay. And now I'm going to put another circle right here. And this is going to be the proton, and I'll have a charge of plus Q or plus E. And this will be the electron, and it'll have a charge of minus E. So what I'm going to tell you is E is equal to 1.602 times 10 to the negative 19th coulombs. And a coulomb's a really big unit of charge. Like you'll see later on in your book, you'll do a calculation of a typical lightning strike, and it's not unreasonable to have a huge, lightning strike that you think is awful and could kill people, which it obviously can. That might not have any more than 100 or a few hundred coulombs of charge. So that gives you an idea how big the coulomb of charge is. Uh, what we also need to know, though, is the distance between the electron and the proton in the hydrogen atom. That's called the Bohr radius, and that's 0.529 times 10 to the negative 10th meters. Of course, you're also going to do this question is going to require you to calculate F gravity, F Coulomb, and then F Coulomb over F gravity. That's the three parts you have to calculate. So if we're doing the gravity one, I also need to let you know that the mass of the electron is 9.109 times 10 to the negative 31 kilograms. And the mass of the proton is 1.6, I think it's 1.67. Is it 1.67 or 1.607? I can't remember. Let's see. I don't have anything right in front of me right now. I think it's 1.607 times 10 to the negative 27 kilograms, but I'll tell you to look at it. Okay, so check that out just to be sure, because I'm not 100% sure I'm remembering exactly. It might be 1.6607 or it might be 1.67, but there's a lot of constants going around in my head right now. So anyways, so that's what you're going to calculate for your extra credit. Anybody have any questions on that? Okay, and I'm going to draw another one right here. Okay. So now that we've got that settled, I want to remind you that the direction of the force is an important thing, and forces still act the same as they did when we learned them in chapters 3 and 4. So they're still vector quantities. So when you're trying to compute the force due to many different things attracting it or repelling it, then you just add them up, but you have to add them up like vectors. Okay. So that's something to keep in mind. Something else to keep in mind, like I said, is like charges repel and unlike charges, in other words, opposite sign charges, attract one another. So that's going to help you figure out what the direction is. Another thing I'm going to tell you is in the Coulomb's force, which says F is equal to K Q1 Q2 over R squared, I never ever ever put in the sign of the charge for Q1 or Q2. Okay. Again, I'm saying with the Coulomb law of force, F equals K Q1 Q2 over R squared, or F equals Q1 Q2 over 4 pi epsilon naught R squared, you never put in the sign of the charge. We're going to later learn an electric field equation that's also called Coulomb's law. I never put the charge in there either. Okay, not to do calculations. Usually, I just use the physics that I understand, which is that like charges repel and unlike charges attract, and that lets me dictate what direction it is. And then I also have to use the rule that says basically a line connecting the center of the charge to either the other charge that's doing the attracting or the place in space. That line is going to be parallel slash anti-parallel to the direction of the force. So I use that. Now, there's also a third version of Coulomb's law, which is for voltage, which is a scalar quantity. Oddly enough, in that case, you do need to make sure you put in the signs because a negative voltage is a lot different than a positive voltage. Okay. So that's just a bunch of caveats I gave you. You can always roll back to this beginning part of the video. We're about at the 6 p.m. mark, so this is a good 40 minutes into the class. Roll back and just write these down if you don't already know them. Okay. And one more thing, charge is conserved. That's a law of physics that we've never found a violation of. So, when you put in a certain amount of charge into some kind of reaction, out will come the exact same amount of charge. And that's never been found to be not true. So we do have a conservation of charge. You'll see some conceptual problems where that'll work. We just have to do some things about making sense of which direction forces point. So, for instance, let me start off by looking at a square. And I'm going to look at a square specifically because this is like one of the problems that I've seen in the homeworks and stuff. So what we can imagine is we're going to have charges at these corners. Let's say this one is a charge of plus Q. Let's say this one is a charge of plus Q. Let's say this one is a charge of plus Q. And let's say this one is a charge of negative Q. Okay. So if we wanted to figure out what the total force is right there in the center, what we know is since this is a square, each charge is exactly the same distance away from the red dot as each other charge. So we already know that, okay? If we imagine putting a charge big Q in there, then the force would be K times Q, big Q that is, K times big Q times little q divided by whatever that distance is squared. That would be the magnitude. But what I'm going to do is I'm going to put a blue underline with that Q. I'm going to put a red underline with this Q. I'm going to put a blue and a red underline with this one. And I'm going to leave the other one black. And what that's going to allow me to do is tell you in which direction this charge positive Q and this charge either the negative Q or one of the positive Qs, what direction is the force between these two? And I'm going to use the color to point that out. So can anybody tell me on charge capital Q, what direction would be the force acting on charge capital Q as just a result of the negative Q? You know which direction it would go? Answers would be right, left, up, down, up and to the right, up and to the left, down and to the left, down and to the right. Anybody have an idea for the force on Q due to negative Q? Okay. Now I haven't at all explained this to you, so it's perfectly fine that no one's answered. And actually, I should probably put up the chat because I see chats are coming in. Someone said down and to the right. Good. We did have someone answer it, so that's good. It actually turns out that the negative Q and the positive Q suggest they're opposite signs. So big Q is going to be attracted to little negative Q. And in fact, the force of attraction is going to be along that line. So these are the lines along which the forces will be parallel. So if I want to talk about what the negative Q is going to do, I'm going to use black and I'm going to say this is the direction of that force. So it's up and to the left. Can everybody make out that arrow is up and to the left along that diagonal? All right. Anybody have an idea uh, on which direction will the force on capital Q act as a result of the blue positive Q? Ooh, that's actually a bad way of writing that. I noticed now that I wrote, let me kill this real quick because this thing is sort of pointing like it's well, I guess it's okay. But remember, that's the force acting on big Q. So that's the main thing that I was worried about. So just keep an eye on that. When I put these arrows on here, those are be the forces on big Q. So let me put it back this way. So maybe you can tell that it's big Q that the force is on. Now, in the case of big Q and positive Q blue there, those two are repulsive. So that's going to make a force that compels capital Q to move away this way. Okay, so now you can see that that blue arrow came from that blue charge, positive Q. Again, positive Q with red, that's going to tend to repel the charge positive Q as well, the capital Q. So this one's going to actually be a force this direction. And I'm drawing it smaller just so it fit. But to be honest with you, all of these would have the same magnitude. So that's the direction for that one. Now, if you look at the positive Q in the bottom left, that's the one that has the red and the blue lines. So again, that's a repulsive force. So what I'm going to say is the force due to this one points this way. And to make the account come up with blue and red, I'll say the force like that. So that is the force due to the positive Q in the lower left-hand side. Does everybody understand what I was showing you with regards to that? Because that's a big thing with this is you have to use Coulomb's law to get the magnitude of the force. Then you have to make triangles and use geometry and stuff like that to try to figure out exactly what components are what, which direction it points, and all that good stuff. And you have to use, trig functions, the sines and the cosines to get the x component or the y component and that sort of thing. But if you can't tell what direction the force is, you're not going to be able to do anything. So anyways, I wanted to make sure I gave you an example like that. Anybody have any questions on that? All right, so let me show you a more advanced problem. And this more advanced problem, I'm going to imagine there is a charge, let's say, of Q1 equals negative 1.11 nanocoulomb. And then I'm going to say over here, there's another charge, and this one's going to be Q2 is equal to positive 1.11 nanocoulombs. Now, in general, whenever you have two equal but opposite charges uh, next to or near each other, then that makes what's called an electric dipole. So what I just created was an electric dipole, and you'll see that popping up over and over again. And later we're going to introduce a magnetic dipole. So I just want to let you know that's what's going to happen. But now what I'm going to do is right dead center between the front of the between them is I'm going to go up at some distance and put another charge right here, and this charge is going to be Q is equal to 1.00 millicoulombs. Okay, so 1.00 millicoulombs. I'm going to tell you that the distance between here and here is 3.00 centimeters, and the distance between here and here is 3.00 centimeters, and the distance between here and the origin again is 4.00 centimeters. So if I go to calculate the force at on capital Q up there at the top, I can see that this is made up of right triangles that are specifically the 3, 4, 5 triangle. So the question is, what is the total force? Whoop, I crossed my L instead of my T. What is the total force on, oh, I said of instead of on Q? Okay, so that's what we're trying to figure out. Now I'm going to box off my solution or my problem. I'm going to box it off using red just so it won't get in the way of my solution. It won't make my solution look a little more confusing or anything. So I'm just boxing all that off, and I'm going to say solution. Whoa, Nelly. My iPad's still in the mode where it tries to make my writing pretty. So, or my drawings pretty. So there's the solution where I'm going to start it. What I'm going to tell you is that we learned that forces add like vector quantities. So I'm going to say the force on Q is what we're asking for. And that's the name I've given it. I've given it F sub Q. But I'm going to use that to point out that the total vector FQ is actually equal to the force on charge Q due to charge Q1, which I'll write with just a 1 next to it, plus the force on Q due to Q2, which I'll write Q sub 2 like that. And that's really the crux of how we solve this. Now, what this means, remember, is that FQ sub x, for instance, in other words, the x component of the resultant force will be FQ1x plus FQ2x. And similarly for y, you'd have FQ y is equal to FQ1y plus FQ2y. And one more thing we need to know, and that thing is that F is equal to K Q over R squared. That's Coulomb's law. So let me start off with just calculating the actual force. Hopefully I have enough room here. I'm going to say FQ1, which is the force on capital Q as a result of charge Q1. Now, in order to do that, I'm going to have to refer to x-axes and y-axes and x components and y components. So I'm going to say this right here is my positive x direction. And let's say this right here is my positive y direction. And then obviously this right here would be my negative x direction. And we also know that according to Coulomb's law, the force of a repulsion or attraction will be along the line connecting the center of masses, or in this case, the center of charges of these charges, which means along that red line somewhere. Okay. So working out the magnitude of FQ1. So I'm just trying to figure out the magnitude of how big a force charge Q1 is causing charge capital Q to feel. So the formula that I'm going to use is going to give me the following result. I'm going to say 8.998 times 10 to the 9th newtons meters squared per Coulomb squared. Now I've got to take charge Q1. Notice I'm not putting in the sign. I'm just writing it as 1.11, and a nanocoulomb is 10 to the negative 9 coulombs. And now I'm going to put big Q, which is 1.00 times 10 to the negative third coulombs. And that's because the M is milli, and milli is 10 to the negative third. And we can see that the triangle that separates basically little lowercase q1 from capital Q is a 3-4-5 triangle, and that tells us that this distance is 5.00 centimeters, and that this angle is 51 point, I want to say 13. No, it's 52 or something like that. Let me check it with my calculator real quick. I'm going to say tangent inverse of 4 divided by 3 is 53.13. That's what it was. I couldn't remember if it was a 1 or a 3 after the 5. So let me kill this real quick. So it's 53.13 degrees. This one was the one I was remembering. That's why I didn't have it on top of my head. But this one is 36.87 degrees. Okay. All right. Now that we have that, we can actually write the r squared in the bottom. And of course, the r is the distance between the two. So that's going to be 5.00 times 10 to the negative 2 meters. And then I got to square that. When I actually do this math, I get 3.9951 newtons. I'm going to double check that calculation. You guys should be doing it as well. So let's see, 8.998 10 to the 9 times 1.11 times 10 to the negative 9 times 1 times 10 to the negative 3 divided by parentheses 5 times 10 to the negative 2 in parentheses, square that, and I get 3.9951. Yep. Okay, so that's the magnitude of that force. And I look at Q1 and capital Q, and I see that they're unlike charges. So specifically, what that means is the force FQ1 is going to act along that red line like I'm drawing right now, and it's going to point this way because it's being attracted to the lowercase q. So it really wants to go to where the lowercase q is. That means it's subjected to a force that points toward the lowercase q. So that force is FQ1. That's the purple one right there. Now I need to break that up into components. What I'm going to do is say red is a negative component and blue is a positive component. We can see that to get from this end of the black vector to this end of the black vector, if I go along axes, I either have to go first to the left and then down, or I have to go down and then to the left. Either way, both of those are negative directions. So now that I have that, I'm going to say that's the x component. I actually drew it a little long. So we're going to say the x component is right about there. That's FQ1x, and it's clearly negative. And then the y component is right here, and that's FQ1y. You can see that's negative as well. So now I'm going to go ahead and compute what that is. FQ1x. It's got to be negative, so I force the negative by putting that sign right there. And now I'm going to take the magnitude of the force, which is 3.9951. Again, the 5 and the 1 are extra digits. They're not sig figs. I can see that clearly this angle right here is clearly 51 point or 53.13. Okay, and it's adjacent to the x component, so that means I'm going to use cosine for x. So I'm going to write 3.9951 times the cosine of 53.13 degrees. And I got to force the negative, remember, so I'm putting the negative down now. 3.99 or 9951 times cosine 53.13, close parentheses, gives me 2.3971. 2.3971, again, carrying two extra sig figs. Now I can do FQ1Y. That also is negative, so I'm going to force the negative. 3.9951 newtons. Now this one, the FQ1Y is opposite the angle 53. So that one means I'm going to use the sine of 53.13. And when I do that, I say 3.9951 times sine 53.13 gives me 3.1961. Again, negative 3.1, oops, 1961 newtons. Now, if you look at, we now have the x and y components of FQ1, but now I want to calculate FQ2. So let me write it, and I think you'll see what's going to happen. I'll write it out. It's 8.998 times 10 to the ninth newtons meters squared per coulomb squared times, again, this is Q2, and the magnitude of the charge Q2 is 1.11 times 10 to the negative ninth coulombs times the charge of capital Q, which is 1.00 times 10 to the negative 3 coulombs. All that is going to be divided by this distance, which is 5.00 centimeters again. So I think y'all can see this and see that, in fact, the magnitude of this force is going to be exactly the same as the magnitude of FQ1. So I'm going to get 3.9951 newtons for the magnitude of the force. Does everybody get that? We shouldn't have to recalculate it, in other words. Now, in this case, you can see that, in fact, the two forces are the two charges are the same sign. So capital Q is being repelled. It's being repelled by lowercase q. So I'm going to choose to draw this vector right here. Oops, I should draw it in black like I did before. I'm going to draw it right here, and I'm going to draw it this way. And that's the force on capital Q due to lowercase q. Notice the magnitude of this vector, which is indicated by its length, is very close, and I meant it to be exactly the same, but is very close to the length of the other one. That's key to understanding. Now, when I draw the components, I see again that the x component is going to be a negative. So this is FQ2x, but the y component is in fact going to be a positive. So this one is FQ2y. We see that's positive. And we again can see that this angle that we wrote up here, 36.87, that's the same as this angle right here. So what I'm going to do is just put a little red line in there. And since it's the same line that I have here, that just means those two are the same angles. Okay? So now all I have to do is calculate the x components and the y component of FQ2. The x component, of course, is going to be a negative, and it's going to be basically 3.9951 newtons times, now you can see this x component, I'm using a slightly different one now. So now what I'm going to have is that angle is 36.87, but the x component is now the sine. So I'm going to say it's the sine of 36.87, which you hopefully already know that means it should be the same as what we got for the x component on the other one, because the cosine of the complementary angle to 36.87 is the sine of 36.87. So that's really why they're called sine versus cosine. So in this case, just to verify, I'm going to do 3.9951 times sine 36.87, and lo and behold, I get 2.3971. So exactly as suggested, negative 2.3971 newtons, and FQ2y has the same sort of scenario. This time we use the cosine of 36.97, or excuse me, 36.87 degrees times 3.995. I don't even need to do it. I can tell it's going to be the same, and I'm going to use the same number, only this time the number is positive because the x component or the y component is actually positive. So I'll put the positive here, and now I look over at my y component that I calculated last time. That was 3.1961. So I'm going to say this is positive 3.1961 newtons. Now, what I wrote so small up there was basically just saying that the x component of f sub q is the x component of fq1 plus the f component of FQ2, the x component of FQ2. Okay, so if I add these components, I'm going to get negative 2.3971 newtons plus negative 2.3971 newtons is equal to negative 2.3971. I'm just going to multiply that by 2, and that's going to give me negative 4.7942 newtons. That's the x component of Q. Similarly, the y component of Q, FQ, is FQ sub y is equal to FQ1 sub y plus FQ2 sub y. The FQ1 sub y is negative 3.1961 newtons. And the FQ2 sub y is positive 3.1961 newtons. So in this case, you see the answer is 0.00 newtons. Okay. So we can now say that we know the entire vector, the vector FQ, the total force on charge Q at the location we've drawn, is in fact purely an x directed vector. So we're going to say its magnitude is 4.79, and I'm going to add those two sig figs in case we need them later, 4.2, and newtons. Notice I didn't write the negative in front of it because a vector can't have, at least not in the non-quantum mechanical world, a vector can't have a negative magnitude. So you just put it as a positive. But the fact that it's a negative x component tells you it points to the left. And if you remember, standard position for trig from trig is measuring a counterclockwise angle from the positive x-axis gives you a positive angle. Or if you did it in a clockwise, it would give you the negative angle. So I need to go completely backwards. So the angle is going to be at 180.0 degrees. That's a perfectly fine way of describing it. But we could also use a unit vector, and I could call this 4 point, actually, let me give myself a little bit of room. I'm going to say negative 4.7942 newtons. All that just times I hat. But of course, in case you always forget whether it's I or J or K or whatever, you can just blindly go ahead and write it as 4.7942 newtons. And instead of calling it I hat, call it X hat. All of those are perfectly valid versions and ways of expressing a force or a vector quantity. Anybody have any questions on that? Okay, so now we can sort of do the exact same thing, and that's also what your book does, is your book says, okay, now that we've calculated it right here at that spot, what if instead of it being here, what if I went straight up here the same distance away and then calculated the force on Q if it was there? So that's really what we're shooting for now. We've only got 10 minutes left. I think we can do it rather quickly. So let's do this one. That was example 1. Let's do example 2. Okay. What is the total force on Q again? Okay. So this time I'm going to put a little mass, a little charge right here. This is going to be Q1 equals negative 1.11 nanocoulombs. And I'm going to go over to here, and then I'm going to go all the way over to here. And I'm going to say Q2 is equal to positive 1.11 nanocoulombs. And I'm going to say this distance is 3.00 centimeters, and this distance is 3.00 centimeters. And then I'm going to go up here and basically say right about here is the charge Q, and this distance is 4.00 centimeters. Okay. But now I'm not putting Q there, so let me erase it. But now I'm going to use that as a reference point to let me know that, oh, it's the same distance away. So Q is actually going to be here, and Q is going to be 1.00 millicoulombs. Okay. I'm going to again make a X and Y axis. So this is going to be my positive X axis. This is going to be my positive Y axis. And this, of course, would be the negative X axis as well. And now I will begin solution. So we know basically the same stuff we knew earlier. So I'm going to go ahead and calculate FQ1. That's equal to 8 point. I'm going to leave all the units off this time because we already seen that they did work out. So 8.998 times 10 to the ninth, 1.11 times 10 to the negative ninth, and then 1.00 times 10 to the negative third. All of that's going to be divided by, now notice this distance from big Q to Q1 is 4.00 centimeters. So I'm going to write 4.00 times 10 to the negative 2 oh, I didn't need to put meters there because I said I was leaving off the units. So it's going to be 4.00 squared. Now, this will give us a different answer than we had before because I've got 4 in the denominator instead of 5. So 8.998 10 to the ninth times 1.11 10 to the negative 9 times 1 10 to the negative 3 divided by 4 10 to the negative 2 squared. And that gave me an answer I did not. No, that's right. This answer gives me 6.2424. And you can now see why I drew the box around the diagram last time. 6.2424. Obviously, I'm carrying 2 extra sig figs again. Now I'm going to box off my diagram again. Okay. So I've got FQ1, and in fact, FQ1, notice the capital Q and the negative, or in the lowercase q1 are opposite charges, so it's actually attracted still. So this force is purely in the Y direction. So that's FQ1. Oop, is that little vector there. So I can now say that FQ1x is equal to 0 newtons, and FQ1y is equal to negative 6.2424 newtons. So we got that. Now I got to calculate FQ2. We've got about 5 minutes left. If anybody needs to leave, of course you can, but make sure you do type in your first and last name before you leave. FQ2 is going to be, again, 8.998 times 10 to the ninth times 1.11 times 10 to the negative ninth times 1.00 times 10 to the negative 3. Whoa. And then I'm going to divide all that by the distance. Now, this time the distance is significantly different. The distance is actually the hypotenuse of a triangle who has one leg 6 and the other leg 4. So I need to work that out a little bit. What I'm going to do is say this is 6.00 centimeters, and this is 4.00 centimeters. And this right here is the angle phi. I'll tell you the angle phi is equal to the inverse tangent of 4, 6 which turns out to be 33.69 degrees. I can also tell you that 4 squared plus 6 squared gives me 52. And now I take the square root of 52, and that gives me 7.21. So the hypotenuse of this guy is 7.211 centimeters. So what I've got to do is put down here 7.211, and actually it's 111, so I could actually do 2 extra sig figs like I've been doing. And that's times 10 to the -2, and then I got to square it. So I can now say 8.998 times 10 to the 9 times 1.11 times 10 to the -9 times 1.0 times 10 to the -3 divided by parentheses 7.211 times 10 to the -2. All that's going to be squared, and I get now 1.9207. So the force is 1.9207 newtons. That's the magnitude. Okay. Berenice is coming in. All right. So now the two charges are actually repulsive. So in this case, I'm going to have the force Q2 is going to be this quantity. I actually meant to write that in black. It's going to be a vector like this, and it's a lot smaller in magnitude than that previous vector because it's so much further away. It's 7.21 away as opposed to 4 away. You can still see exactly what geometry goes into this. For instance, the x component is clearly a negative, and the y component is clearly a positive. And this angle right here is 33.69 degrees. So now all I have to do is say FQ2 sub x is going to be 1.9207 newtons. It's going to be a negative, and it's going to be times cosine of 33.69 degrees. So I'll say times cosine 33.69, and that gives me negative 1.5981 newtons is the x component. FQ2y, that one's going to be a positive, so I force the positive. It's 1.9207 newtons times, that's an opposite side, so that's going to be the sine of 33.69 degrees, forcing the positive here. So 1.9207 times sine 33.69 is equal to 1.0654 newtons. So FQ sub x is 0.00 newtons for the FQ1x plus negative 1.591 newtons, which gives me negative 1.591 newtons for the x component. The y component, FQ, whoa, FQ y is going to be the y component of FQ1, which would be negative 6.2424 newtons plus positive 1.0654 newtons. So this one's going to be negative 6.2424 plus 1.0654. That gives me 5.1770. So that's negative 5.1770. Okay, so that's the y component. So what we can say now is I can draw a x and y coordinate system, but the third quadrant's the most important one here. So that's going to be my positive x-axis. That's going to be my positive y-axis. And what I'm going to have is a x component that is a little bit bigger than 1.5. And then I'm going to have a y component that is actually still negative, even though that other one was positive, it's still going to be a negative. So it's going to be quite a bit bigger. This side being 5.1770, and this side being 1.5981, and this angle right here being 5. So I can figure out, we're almost done. You guys are free to go. It just met 6:40. So I'm going to finish this out and then write it in its appropriate form. But if you need to split, go ahead. I understand. Phi is going to be the tangent inverse of 5.1770 over 1.597, or excuse me, 5981. And that's going to give me tangent inverse 5.177 divided by 1.5981, close parentheses, and that gave me, oops, I did tangent instead of inverse tangent, 5.1, 5.177 divided by 1.5981. That gives me 72.84 degrees. So carrying two extra sig figs there, I can use the Pythagorean theorem to figure out what FQ is, the magnitude, but I got to pay attention again to squaring the 5.177 and the 1.591. It turns out when I square the 1.5981, knowing I only have three sig figs, that allows me to keep up to the hundredths place. But when I square 5.177, that comes out to be like 25 or 26 and some change. So two of the sig figs are in the actual number to the left of the decimal, which means it's only good to the 10th decimal place. But when you add one that's 25-ish and the other one that's well under that, you still have even rounding it to one decimal place, you still have three sig figs. So I can ultimately still get three sig figs. All I have to do is take 1.5981, and I'm going to square that, plus 5.177, and I'm going to square that, and that gives me 29.3552. Now I'm going to take the square root of that, and that gives me 5.4180 newtons, and that's the magnitude of the force. Okay, so what we're going to finally say is that the force FQ is going to be 5.4180 newtons at, now this angle is 72.845, but that's after you've gone a whole 180. So this is going to be 252.845 degrees in standard position. But you could also write it using your x hats or I hats, in which case I'm going to say negative 1.5981 newtons x hat plus negative 5.1770 newtons y hat. And that's it. I got to put a vector symbol over top of that F for the name. And now that's it. Anybody have any questions with that? All right. You guys are free to go. As I said, I know I did get one of my other students come in for possibly an office hour. I'm going to wait here till the last person leaves. So thanks for coming, everybody. And any questions?
No, have a good night.
Okay, see you, Giovanni.
I finally got into the homework, but I knew this and I knew it was gonna happen. Everything's reset. So, and all my grades and Canvas are gone. So
Oh,
that's
are you serious?
super stressful. And like it's like past due. And if I do it, it's like takes the 5 points off a day.
Don't
And
worry
I
about it. Try to do it. Maybe like, we're doing a roughly a chapter a week. See if you can do an extra chapter each week.
okay.
And don't worry about losing points or anything. And I just want you to do them for to make sure you're up to speed on it. If you got the chance to do them before, you don't need to redo them. I'm not going to take off points for you. I'll
I
fix it.
think I have my notes from chapter 17 because I did it all on paper. So it
Mhm.
wouldn't be if it was the same thing, it wouldn't be hard for me to go back in and like put those answers back in because I have it all.
No, that
Um,
should yeah, that should be the same thing. Sometimes they'll change some of the numbers, but it's still the same problems.
okay. And then for 18, are you gonna extend the due date or because I didn't quite understand what you said at the beginning, if you were or were not going to.
I told everybody I could do 19. 18's
Okay.
already been done, but if you need 19, I'm not going to take off points for you having 18 done late. So don't worry about that. If you haven't done it, just do it and let me know when you get it done, and I'll probably just discount any points taken off for lateness.
Okay. I don't know if I have to go look through my iPad notes. I don't know if I have everything from 18. But I can definitely put 17 in there. And then do you want me to send you a text messages with like, hey, I was able to finish it, but it says it's late and with like a reminder of why?
If you send me that, that'd be great. But again, since you already did 17 and 18, I don't mind if you don't do it. Okay. I'm not going to take off points for those two. Just like I said, I know your situation. I knew what happened. I know you had done them before. So I'm not going to count that off. We'll just start counting your average from there. And again, I'll talk to you about 2 or 3 weeks before the final of the course, and we'll make out some kind of arrangement to see if you're happy with your homework grade. So if you want to redo them, then by all means do them. But if you already did them, I'm not going to require you to, and I'm not going to give you a 0 for those, at least those two chapters.
Okay.
Okay.
Okay. Alrighty.
Go ahead,
Thank
Hannah.
you. I'm going to lab.
Yeah. Have a good one.
Thank you, you too.
Bye bye.
Bye.
Hey, Berenice, what's going on?
Hi, Professor Younger. Can you hear me?
I can. What's up?
Awesome. So I have some questions
Okay.
from for chapter 3 and from the practice test for the exam we have coming up.
Okay.
So yeah, I just wanted to talk to you
Okay. So
about it.
do I need to stop recording? Are we talking about, private stuff, your grades and all that kind of stuff? Because I'll go ahead and kill it. But if we're solving
If
physics
you don't
problems,
mind.
I'm recording it.
Yeah, there are some. We can get right to the problems, and I can like talk to you about other stuff later if you want.
Okay. Okay.
Yeah.
Go for it.
Yep. Okay, so I'll start sharing my screen here. Oh, it says that.
I just changed it. I hope
Okay.
I got there quick enough, but it
Let's
appears I had.
see. Oh, there we go. Now it works. Okay. I will do. May have to switch it. Which one is which? Okay, we'll start with this chapter 3 practice. Okay, can you see this?
Uh-huh.
Okay. All right. So with chapter 3, like I understand the basic concept of like what a vector is.
Mm-hmm.
Um, but when it came to and like with the problems, I feel like I understand certain elements of how to set it up. But
Right.
then like when I actually go to solve it, like I'm missing pieces and I just end up getting the
Gotcha.
answers wrong. So I did, yeah. I just wanted some to kind of like work through some of these with you
Okay.
just so I can help
Let's
solidify it so I'm not
let's start
lost.
with that first one. I know you got that one right, but I want to
Mhm,
point something out. It says the magnitude of a vector can be less than the magnitude of one of its components. When we say components, we specifically mean like an X and Y component, so they're perpendicular to each other.
mhm,
So it turns out that if you take two perpendicular numbers, components, you have to square each of their magnitudes, add them, and then take the square root. We know what that math does, and it turns out that the magnitude of the vector is bigger than either of the two, but it's smaller than or equal to the sum of the two. So what I mean, like if one component's 1 and another component's 5, the most it could be is 1 plus 5 is 6, and the least it could be is 5 minus 1 is 4. So
Hmm.
that's just something that they sort of expect you to know from high school algebra / geometry. So just being prepared for that. But other than that, you're good to go. You got that one right.
Okay, yeah, the only one. So hoping to turn that around. Okay, but so the magnitude is going to be greater
Yeah,
than
or
one of its
it could
components
be
for both of
equal
them.
to one of its components, but that means it doesn't have the other component. So yeah,
Okay, which makes sense if, like, I did see some of those vectors where, like, it was either straight it was, like, along one of the axes only. So,
exactly.
okay, so it can't be less. Alright. Yeah, thank you for
Okay.
clarifying that because I was just kinda, like, using best guess there,
Yeah.
for that one. Okay, for this one, so I'll try to find my notes on how I solve
The
this
swimmer
problem.
heading directly across a river 200 meters wide reaches the opposite bank in 6 minutes 40 seconds. She is swept downstream 480 meters. How fast can she swim in still water? Okay, so I'm going to draw a picture on. I'm just doing some paper right now just to get used to it and get a sense of it. The width of the river is 200 meters. She ends up leaving and then going downriver by 480 meters. And basically, what that means is you draw a diagonal line from one bank to the other bank like this, where the width left right is 480 and the height up and down is 200 meters.
Okay.
And that's
Alright, looks
the
like I had that.
water to Earth.
Okay.
So there's a couple ways. It's asking how fast can she swim in still water. So what we're assuming is she swam sort of at her fastest, and her fastest took 6 minutes and 40 seconds to cross this 200 meters. Now, what you can imagine is she actually fought and to swim straight ahead, and she just let the stream wash her downstream at whatever rate it's going. So if that's the case, then she swam directly ahead, and the vertical component, the component of her velocity that goes from one bank to the other perpendicular to the banks,
Mhm.
component has to be 200 meters divided by 6 minutes 40 seconds.
Oh, okay. See, I don't know why I did this, but I had the vertical component as the 200 meters.
Mm-hmm.
I had the horizontal one as the 280 meters, and then I guess in my mind, I was like, "Well, she's trying to swim straight across, but it's carrying her, like, downstream." So I drew a diagonal line and made that 6 minutes, 40 seconds. Don't know
Gotcha.
why I did that, but okay. So you're dividing the 200 meters by the
Yeah,
time.
I took the 6 minutes, which would be 6 times 60. That should be 360, right? And then I add 40 to it. 6 times 60.
Alright, to make it
60 plus 40. I got 400 for that. So
mm,
yeah. Um,
calculator.
now that's the problem though. I don't know if that's really what they mean by the oh, you said okay, gotcha. And that is one of the answers. So that makes me feel a little better. Uh, and this would be chapter 3, I bet.
Yes, sir. Yeah, chapter 3.
Okay. I'm gonna pull it up to check, make sure I got everything right. So uh,
So did you do you added the 40 seconds to
to the 6 minutes. Yes.
okay, so you have 400. That's what I had, 400 seconds.
Yep. And 200 meters.
Okay. Okay, and that's giving us the velocity.
Yep. That gives you the average velocity directly across. I'm trying to
Mhm.
remember what yours looks like right quick. See, okay. So this is a swimmer heading. I'm trying to pull up just to make sure that we're on the same page and that I fully understood the problem, but I think that's pretty much the only way we can solve it.
So was I correct in like thinking in terms of I need to draw a diagonal
Right.
from kind of like as, origin to um like the tip of the y component. That's 200 meters.
Yes.
Okay, but I just had the time on there and it should have been like the 200 meters over the 400 seconds for the
Yeah, so that's the same sort of diagram that I had.
Mhm.
So you can see I pointed the 200 meters up and down like that's across the river, and then 480 is what it went diagonally down to the right, basically. But the hypotenuse of that right triangle is really how far she went. What did you
Uh-huh.
do? What did you do with that number to try to get the 1 point or to get the 1.2 that you came up with?
Okay, what I had done ah, so I basically um because what was the question? It's asking for
How
how
fast did
fast
she
you can
swim
swim.
in
So
still
I
water?
basically was solving for the would it be resultant vector?
Hmm.
Like that yeah, so I put the 480 meters and the 200 meters into, like, the Pythagorean formula
Hmm.
as if I were solving for V.
Gotcha.
Yeah, and then what did I do after that? Wait, how did I do this? Sorry, I'm, like, looking for my notes here.
No problem.
A little 0.2 meters per second. Hmm,
Yeah, I think I figured out what you did. No, did you get, is it possible that you slightly got a little different number and you just said, well, that's close enough? Because
let's see. I did oh, hold on, I erased prematurely here.
I got 520 meters using the Pythagorean theorem.
Yeah, so I did 520 meters. I had 520 meters in
Then you divided it by 400 seconds.
yes. You know what I think I did? I think I got the math wrong here. Because I got 154 seconds, which clearly is not the right
Ah,
thing.
yeah, I gotcha.
So, yeah, but I did at some point divide the 200 meters by wait, 200 meters? What?
520 meters. Yeah, is what it should have been. The 200
Yeah.
is the way I did it, which
Mhm,
basically just said that the person did their best to swim straight across the river. So
mhm,
they didn't try to turn and go upriver or turn and go downriver at all. They swam perfectly perpendicular to the flow of the
mhm.
river. And that they did so swimming at their fastest, and that meant they went a distance of 200 meters vertically or across the river in a time of 400 seconds, and that gave me the
Mhm.
half meter per second, so 0.5 meters per second. So that's what she can move in the calm water with no current or something like that.
Okay. So the 200 meters over the 400 seconds is like, okay, that's the calm water. Now, for the other one though, we
Mhm.
we are drawing that diagonal there. We want to know the vector, the velocity vector.
You talk about for
Because it's accounting
question
for like the
three.
downstream.
You talk about for another part of question two, or are you talking about the new question three?
Oh no, for question two.
Oh, gotcha. So if you wanted something, If you wanted something else, like maybe you wanted to know how fast you can go or how fast the water's going or something like that, you could
Mhm.
use that as well. For instance, the fact that she went 480 meters downstream, that means the stream moved 480 meters from like right to left, say. And if you take that 480 and divide it by 400, that'll give you the velocity of the water.
Oh, okay. So basically, I didn't even need to find the distance of that like hypotenuse.
Nope.
I just need okay.
Yeah, and that one's it seems trivial because it's so few words to ask the question, but it's conceptually kind of difficult. What you've got to make sense of is the person swimming in some sense parallel with the stream,
Mhm.
in some sense anti-parallel with the stream, or is she swimming perpendicular to the stream? I assume she was trying to get across in the fastest time she could, which would mean she's going to try to swim completely perpendicular to the current. And then using that, that's how I was able to say, well, she would go in that direction. She'd go a distance of 200 meters in 400 seconds, and that's their best. So
Okay.
that's not an easy plug and
Uh-huh.
change for the problem. It takes a little thought to get through it.
Okay. So the last one here would be the correct answer.
Yes, yes.
Got it. All right. Just complicating it there. All right. Question 3.
Okay. A child throws the ball with initial speed of 8 meters per second at a 40-degree angle above the horizon, or horizontal, excuse me. The ball leaves her hand 1 meter above the ground. What is the magnitude of the ball's velocity just before it hits the ground? Okay. So what you've got to do is you first got to figure out the x and y components of her initial velocity. Did you do that already?
Yes.
So you did like 8 times the cosine of 40 and you had it in degree mode.
Yeah. So, and that was for the x component.
Uh-huh. And then you did 8 times the sine of 40 and got the y component, right?
Yes, sir.
Okay. I get 5.14 for the y component, 5.1423.
Yes, that's what I got.
Okay. So what you want to do now is you want to write an equation for y, and it's the same equation I wrote every time for y. It's negative 4.90 t squared. In this case, it'd be plus 5.1423 t, and I would say plus 1.00 because they said she threw it from a height of 1 meter above the ground.
Okay.
Okay. So I've got y equals negative 4.90 t squared plus 5.1423 t plus 1.00.
Mhm.
Now, what
And
we want to know, oh, go ahead.
oh, I was just going to say that that's how I had it set up too.
Okay.
Um, before we continue, could you kind of explain just to make sure that I'm grasping it well?
Okay.
Kind of like why we're using that formula.
Okay. So let me go ahead and pull my notes out. I'm going to steal the screen again. So let me share screen with you.
Do I need to stop sharing?
We'll see. I think it pops up and it'll allow you to choose which one you want to look at. So you should be able to see it full size. If you can't see it big enough, then yeah, go ahead and stop sharing yours. But I think it'll allow you to choose mine as the bigger one. So what I'm going to do is I'm going to assume the origin is at ground level,
Mhm.
and she is firing at an angle of 40 degrees from a height of 1.00 meters, and the velocity v0 is equal to, was it 4 meters per second?
V0 is 8
Eight.
meters per second. Yeah. And am I supposed to see the screen?
Yeah, is it not showing it?
No, sir.
Okay, so you might be able to look where it says screen sharing and
Screen
hold your mouse
sharing.
by it, and it should let you pick which screen you want to see.
Oh. Um,
You don't see that?
no, I do not. Let me.
Okay, so what I'm going to do now is I'm going to click one share at a time. Let's do yes and see. Okay, so it just kicked me out and you out. That's okay. I'm going to go ahead and share it again now.
Okay, I see a box. It's black right now.
Okay, so yeah,
Oh, there
that's
we go.
my X coordinate and that's my Y coordinate. And what we're going to assume is the ball is going to go like this and land some distance over here. And what they want to know is V final equals question mark. Okay. So what we discovered when we learned that A was equal to dx dt, or excuse me, dv dt, is that V would be equal to V0 plus AT after we solve the differential equation. And then realizing that V is equal to dx dt, we were able to put together that X would be 1/2 AT squared plus V0t plus X0. So that was the differential equation process that we solved when we considered A being a constant. So
Mhm.
if A is a constant and that's your acceleration and it's a constant acceleration, and your initial velocity is v0 and your initial position is x0, then this equation 1/2 at squared plus v0t plus x0 will always work. So I did that for X, but it can be held true for Y as well. So I'm going to say Y is equal to 1/2 AT squared plus V0Y times T, which means I should put an X on the V0 over there, plus Y0. So that's why I use that Y equation for both the X and the Y. So now I can say y of t is going to be equal to, I drew the coordinate system such that up is the positive y direction. That means the acceleration's got to be negative 9.8. And if you
Okay.
multiply negative 9.8 times 1/2, you get negative 4.90. Now, in our case, we got the velocity was 5.143 in the y direction. So I'm going
Mhm.
to say 5.1423 t plus 1.00, and I'll leave off that m because I'm leaving all the units off right now. So that's y as a function of time for this projectile. X as a function of time is essentially the same thing, except the acceleration in the x direction is 0. So you just get 8 times the cosine of 40. 8 times cosine 40. That gives me 6.1283. So I'm going to say 6.1284 times t. And I assumed it started at x0 equals 0. So that's the whole expression for the x. We're probably not even going to need it for this problem, but I just wanted to show you that's where that came from.
Okay.
Does that make sense now? You can see it's the same equation in both cases, and it just comes from integrating a equals a constant twice.
Yes, sir.
Now, when we get to the ground level, we're going to need the velocity. And we're going to need the velocity in the x direction. We're going to need the velocity in the y direction. Then we're going to have to take the Pythagorean theorem of both of them, using them, and that'll give us the total velocity. Does that make sense?
Um, let's see. Yes, I'm kind of understanding.
Yeah, because that little velocity there will have an x component and a y component.
Mhm.
And this is just a split second before it hits the ground. So we're not, we're not thinking about the ground hitting it and slowing it down or anything like that. We're trying to catch it just before it hits the ground. Now, the premise of projectile motion was that there's no air resistance. So the velocity in the x direction is just a constant. So we can already say that v final sub x is 6.1284 meters per second, using way more sig figs than I'm justified, but we know that, okay? We can also know that since it's given an extra 1 meter of height when she launched it, that it's going to be going a little bit faster than the 5.1423 in the downward direction. And you might even realize that in basically in 1 second, you move on the order of 0.49, or excuse me, 4.90 meters. Or excuse me, it's about that. So you could divide that by 5 and get an estimate. That would be fine, but that's not really what we're shooting for here. What we want to do is figure out at what time will the ball hit the ground, and then we'll use that time to figure out what's the velocity when the ball hits the ground.
Okay.
Alternatively, you might be able to use v squared equals v0 squared plus 2a. In this case, I'd have to put a y there and a y there and a y there, and this would be y minus y0, like that. So in principle, that might be able to work. We'll try it because that's a lot easier. But I would normally start off with the blue equation, the negative 4.90 t squared, solve for t, and then come back and use the a equals v final minus v initial over t to find out what the final velocity is. But let's go ahead and try this. What I want to know is the final velocity. So vy squared is going to equal 5.1423 meters per second squared plus 2. The acceleration is negative 9.80 meters per second every second. And the change in y is the y, which is 0, minus the y0, which is 1. So what we're going to do here is we're going to say 0 minus 1.00 meters. So we're ultimately going to actually add it. So I'm going to say 5.1423 squared is equal to 26.4432 meters squared per second squared. And then 2 times 9.8 times negative 9.8 times negative 1 is positive 19.60 meters squared per second squared. So I'm going to say add that to the 9.8. So 2 times 9.8, I'm going to add that to the 26.44. And that gives me 46.0432 meters squared per second squared. That means v sub y, that means the final y velocity in the y direction is the square root of that 46.0432 meters squared per second squared. So I'll take the square root of that. And I'm taking technically the negative square root because it's going to be going down. So I'll call that negative 6.7855 meters per second. So this one's supposed to be 6.7855 meters per second. And that's the quickest, dirtiest way you could do it. It specifically asked for what? The magnitude of the final velocity, or did it ask for the actual magnitude and direction, or what?
Yeah, the magnitude of the velocity just before it hits the ground.
Okay. So if we need the magnitude, then the magnitude of the final velocity is just v equals the square root of 6.1284 meters per second squared plus negative 6.7856. You really don't have to put that negative in there, but I wanted to make sure you knew that it is being dealt with. So I'm going to square this 6.7856, and I'm going to add to it 6.1284 squared. That's going to give me the square root of 83.6005. And now I'm going to take the square root of that. And that gives me 9.1433 meters per second. So that should be the magnitude. Did they have as one of the options like 9.1 or something like that?
Yes, 9.14 was an option.
Okay, I suspect that's exactly the answer. Would you like me to go ahead and show you how we would do it the original way I was saying?
Yes, sir, because that is the way that I was trying to approach it at first.
Mm-hmm.
So I would like to see how
Okay, so what we're
that
going to
compares.
do is we're going to say y equals 0 at t equals question mark. That's what we're trying to do. So I'm going to say that means 0 is equal to negative 4.90 t squared plus 5.1423 t plus 1.00. That means we're going to use the Pythagorean theorem and, or excuse me, the quadratic formula.
Mhm.
So a x squared plus bx plus c is equal to 0. That means we're expecting all sums. And then that says x would be negative b plus or minus the square root of b squared minus 4 times a times c over 2a. So this is going to be negative 5.1423 plus or minus the square root 5.1423 squared minus 4 times a, which is negative 4.90 times c, which is 1.00, like that. And then all this will be over 2a, which is negative 9.80. So 5.1423 squared. Notice the two negatives make it plus. So I want to say plus 4 times 4.90. That gives me 46.043. So under the square root is 46.0432. Now I got to take the square root of that. So this is going to give me negative 5.1423 plus or minus 6.7. That's a really bad looking 6.7855 and then all this will be divided by negative 9.80. So if I do negative 5.14 minus 6.27, that's going to give me a negative number, and then divided by a negative number gives me a positive. So that's an actual reasonable answer. So I'm going
Mhm.
to say, go ahead.
Oh, I was just saying, yeah, that I was tracking.
Okay, so I'm going to do negative 5.1423, and then I'm going to say minus 6.78552. That gives me negative 11.9278. Now I'm going to divide that by negative 9.8. And that gives me 1.2171 seconds is what that should be. Now the other answer would be negative 5 plus positive 6. So that's going to give you a positive, and you divide it by a negative. That's going to give you a negative. So this must be the right answer for the time.
Okay.
Now that I have the time, I can go ahead and, since this will make it crystal clear, I can draw in a little circle and come way back here and say A is equal to V final minus V initial over time. So V final is equal to V0 plus AT. I'm going to use that for just the Y component of velocity because the X component is not going to change. So the V final in the Y direction will be equal to the 5.1423, which was upward, so it was positive initially, plus the acceleration is negative 9.80, so that's on purpose. And then I'm going to say times 1.2171, carrying just way more digits than necessary, just to keep it honest. So I'm going to say 5.1423 minus parentheses 9.8 times 1.2171 close parentheses. That gives me negative 6.7853 meters per second. Notice that looks very close to what we got doing it the other way. So that's right on the money.
Okay. And that's for the Y component.
Yeah, so you still have to take the X component, which is a 6.1284, square that, take this Y component, square that, add them, take the square root, and that'll give you the 9.14.
Okay. So to see where my confusion came from, because I did get the same time
Mhm.
that you got. Just my decimal places were a little bit different because I didn't carry as many
All
sig
right.
figs. But I used for the velocity formula for V initial, I used the 8 meters per second.
Ah, yeah,
Don't know
yeah.
why that was my
Break it
thought
down to
process.
components. Yeah. You might want to make
Mhm,
like some notes and just say projectile motion problem. First thing, break velocity, initial velocity up into X and Y components.
mhm,
That'll help you a lot. But there is some times where you don't have to do it. So, for instance, when they say something's launched off of a horizontal or flat level surface, then
mhm.
the initial velocity is just the X component, and there's no Y component whatsoever. So sometimes that's the case. But other than that, yeah, you're always going to have to take the sine and the cosine and figure out what the X and Y components are.
Okay, and for the last formula that we used, so, like, the V final equals, V initial plus
Mhm.
AT, um,
That was
okay,
actually the first equation we got when we first integrated A equals a constant equals dv dt. Because when you integrate
mhm,
with respect to t, it just becomes at plus a constant. And that, of course, is equal to the integral of dv, which is just plain v. So if you use the condition that at t equals 0, v is equal to v0, then the constant of integration has to be v0. That's where that equation came from.
okay. I think I just got confused with identifying what the different, like, um, pieces were
Right.
in here because, like, I got confused and I saw, like, the V initial, and then I'm looking back at the original, like, in V initial that was given of the 8 meters per second. So,
Right.
like, I wasn't quite thinking through
Yeah.
that.
So when you think of a projectile motion problem, you want to think of it like an angle, and then there's going to be a little X component right here and a Y component right here.
Mhm,
And then you can sort of picture two vectors on the little ball as it's flying. And the horizontal vectors, the X component of velocity, that one's never going to change length. It just keeps the same. But the cool thing is that little vertical one, it's going to
mhm,
shrink, 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 get to 0, and then shrink, 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 or excuse me, grow, grow, grow downward. So it's actually going to get back to the same length that it had, but it's going to be pointing down now instead of up. And
okay.
that's what's going on. And maybe envisioning that while you're thinking about the projectile flying might be better at helping you keep track of what's what when you're trying to solve the problem and you get in the middle of it and that sort of thing.
Right. Okay. I see. I don't know how much longer you have on here. I don't want to.
Yeah, I'm gonna have to split.
Okay.
I will be in early tomorrow if you want to see me before class. I'm
Okay.
in the office.
Yes, sir. I probably won't be able to make it just because I'm on a tight schedule in the mornings with ROTC.
Oh yeah,
Um, but I do plan on joining your Thursday Zoom
gotcha. You're
meeting.
welcome
Yeah,
to
this
do
was
that.
very
You're
helpful.
also, if you're around during the morning, my first class tomorrow is a lab from 9 to 11:50. And basically from about 9:30, 9:45 on, I'm available for free then too. So you could also stop by if unless you have a class at that time, you can stop by then as well. Just I'd be in one of the labs.
Yes, sir.
Okay.
Well, I do appreciate your time. This was helpful.
Oh,
Because
actually,
as
you're
I
in that
said,
lab.
it's like the little mistakes for me. I'm just like
Yeah, they'll bite you.
that like mess me up in the end.
Yep. No problem. Well, you'll get it worked out. Don't worry. And we got a little while for your next test. So have a good evening. Thanks
All right.
for coming in.
Thank you. You as well.
You're welcome. Talk to you later.
Bye.
Bye-bye.